Hello, ladies and gentlemen. Good morning. I've got very little time to talk about this. I've made two other videos, and I'm going to put them in my archives because, well, I kind of got a couple things backward, and I was trying to find the first Jupiterian stripes that I ever mapped on my particular program of Google Earth. And for some reason, for the life of me, I can't figure out what happened to them. But I have the others. I have the third and the second and the third, and then what I refer to as the theoretical Pangaean stripes. So anyway, we can go into more detail on that later. Right now, this is about impactors on the Earth, and I think there's a great big misunderstanding where folks just aren't seeing where these craters actually impacted and how many really did hit the Earth. Naturally, we all assume very many hit the Earth, but the scars are still there, and we just have to know how to look for them. So that's what I'm trying to establish, is a means of identifying these different... Shush, Boomer. Is your toy under there? One moment, please. I have to get my dog's toy. No, you're not. This is not your toy, Boomer. This is Doodle's toy. Boomers can't play with Doodle toys. Go find your other toy. Sorry, folks. He gets that way sometimes. All right. So here's my first PowerPoint. In my first PowerPoint, basically, I'm trying to speak quickly because there's a lot of material I want to cover. This is the largest impactor that ever struck the Earth, the one in the South China Sea. This is the one that made the Earth do a whole bunch of crazy things. And at the minimum here, as you can see, I'm pointing to the screen of my computer. You notice with my mouse, if you follow it right here in the calculator, it's 8,417. So that's basically 8.4 kilometers. That's an established minimum of the possibility of the diameter of the impactor when it struck. And I'm going to describe how I go into details on figuring that out. I don't just pull that kind of information out of my butt. I actually try to use some scientific data to help. Typically, when you find a B2W or a blast bow wave, there is like this ratio distance, regardless of how large the impactor is, regardless of how large the munition is. The B2W always has the same, almost the exact same, I won't say the same because it's probably never the same, but almost the exact same signature. So you have the blast bow wave coming out like this, and then you have the blast ring going around it, and the distance from the furthest forward point of the blast bow ring to the blast ring is almost always, by ratio, the same distance. As we look at this, it looks like the blast bow ring's right on top of the B2W. And the thing about that is, as I was suggesting earlier, or maybe not quite yet because it might be in one of the videos I set aside. So if you have a blast bow ring, the birdie shape, coming like a birdie from badminton, coming down like this, the distance from this leftmost limit to the rightmost limit is going to be based on the angle of the trajectory. So if it's a direct hit, this gets wide, and the more direct it is, the wider this gets, right? And as it gets wider, it ends up becoming just a big circle. So you don't see it. It's bullseye, like Bermuda Rise. Bermuda Rise is a central peak to a impactor, and the blast ring is huge. It goes all the way up to, pretty much all the way up to the eastern coast of the United States. People are going to think I'm crazy, but I'm trying to tell you, look at it. You don't know until you look at it. And when you start looking at everything I'm showing you, you're going to start to see how repetitive everything I'm describing begins to appear. All right, and top that. The artillery's been doing, figuring out where the enemy is based on reading doing crater analysis. So it's effective. It's extremely effective, and we actually know what we're talking about. And the Earth has what we call a deflection. Anytime you have some sort of a round, especially with meteors, you have a round that hits the atmosphere. It's like a rock hitting the hitting the pond. It goes at an angle here, and the friction from the pond is going to redirect that object as it's going into the pond. Deflection. You get deflection in our atmosphere, and that's where you get your B2Ws from. That doesn't always happen, like I said. You have the Bermuda Rise, which is a central peak, which means that was a bullseye. That one hit right there. Boop! Just like the moon. All right. And I'm pretty sure I've covered how you describe blast rings in my videos. If not, please ask questions. I can go ahead and explain how the blast rings come to appear. All right, so right here we basically determined that 7% of 120,247.98 meters is equal to 8,417 meters. So that means that if the impactor is 7% less the size of the blast ring, in this case I'm determining that this is possibly the blast ring, but because it lines right up with, you notice this coming right here, that's my blast bow wave. The blast ring's right on top of the blast bow wave. So if the blast ring is right on top of the blast bow wave, one thing is for certain, that's probably not the blast ring. So you might actually say that by ratio, the blast ring would, if this is my B2W coming through here, and I'll outline it later, right around here is going to be my true blast ring. And you can see a shape right there. But the oddness about this shape is there's no circle. So, but this was an extremely violent impact. It had an extremely huge effect on the Earth's surface in very many ways. So you can pretty much expect that wouldn't be there anymore. So basically, it ended up causing a vortex as it struck the Earth. So it takes all that material, like water in the pond, and goes, throws it out. And then as this material from underneath that was displaced begins to fill in that void, because it goes out like this and comes back in, okay? Boom, recycle. All right, so it's coming back in. It fills up that void. And as it's filling up that void, guess what? It goes into a rotation. In this case, it went into the rotation the opposite direction. It went into counterclockwise rotation. What causes it to go into a rotational direction? In this case, the North Banda Basin primary vortex is already rotating clockwise. So that means that the material that filled in was going to be forced by some, a kind of like a gear relationship, and goes in the absolute opposite direction. And this becomes then a binary relationship between those two vortices. Okay, so now we're looking at this one. So I tell you right there, blah, 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 blah. Diameter impactor, blah, blah, blah. But that's the minimum, folks. If we actually take our blast bow or our blast ring and put it out here by ratio where we would normally expect to find it, that impactor is going to get bigger. All right, so this is just the minimum size of that impactor, 8.4. The one that just flew by us, if it was a mile, I think they said it was like a mile long. If it was a mile long, that means it's about 1.6 kilometers in length, right? So this impactor was at least 5 times the size of that impactor. All right, this is Meteor Crater. This is where I come up with my information. So this is determined by scientists who have looked at this crater and said, I think that the meteor that hit that crater was about anywhere from 30 to 40 meters in diameter. So that means that 40, we're going to go with the average of that, which is in the middle, 40. And 40 meter diameter multiplied by 100 divided by 585.7 meters, that is the radius of this impact site, as you can see right here from Google Earth. 4,000 equals 4,000 meters divided by 585.7 meters equals 7%. Ta-da! There's my 7%. See, I didn't pull that one out of my ass. Now here's some interesting things about this. We look at this great big circle and we're saying, hey, that was one impactor. No, I'm sorry, folks, it was not one impactor. It broke up. It either broke up or it was a series of small impactors, and they had a very tight sheaf, like a shot group that was like, bam. I wish I could shoot a target like that. Pop, 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 right there in the middle of it, right? Yeah, there you go, all you gun guys out there. All right, so it has at least four, not at least four, about four other blast rings within the circle. You can even see them right here. There's two. Okay, they broke up, folks. But this was a depth burst. That means it penetrated the ground before it exploded. All right, now we're going up here. And we have... don't get me wrong. That's actually only one blast ring. It has more. This was a far larger area affected by it, but no way comparison to the South China Sea impactor in Indonesia. Right, there we go. Moving right along. Now you can see my stuff right here. So as this material filled back in the void, okay, and there may have, I'm not saying that none of this continental mass was here. There could have been continental mass there, but it definitely warped the shape of that mass like you wouldn't believe. And it warped the Eurasian continent quite a bit too. So as we're looking at this, it comes back in and it fills up and it starts going this way. Now, the waves that we see here, ladies and gentlemen, these waves, you could be standing on the shore of, I mean, if your vision was really that good, you could be standing on the shore of Australia and watch these waves move in. You could be in the International Space Station, ISS, and watch this take place on the planet's surface. That's how freaky and scary it is. People were not, I mean, you know, if it was a snake, it would bite you. If it was a bear in the woods hiding behind a tree, and you just blindly walked right up to it, it's going to eat you. Okay, so that's a kind of cool surprise. It's cool because it shows a whole new dynamic to the Earth. I think. Excuse me. I think I'm trying to say this as quickly as I can. It's going to have to be in parts. I only have so much time in the morning to talk. I'm a morning person, so when I get home from work, I'm just like. Ugh. Anyway, I'm trying to do this because, yeah, okay, stop. Okay, so here we go. Now we're going counterclockwise, folks. We're right down here. We have the pentagonal shape of the North Banda Basin, which this is not necessarily right smack in the center of the North Banda Basin vortex, which tells me that when this had occurred, it very likely pushed that core, that center of that vortex down further toward the south. And then you have what we developed from here to here, a binary relationship in two vortices. Okay, there's a lot more that goes to this than this, folks. Don't get me wrong. That's why there's so much activity here. Old wounds, sometimes, old wounds never heal. And this is one wound, ladies and gentlemen, that hasn't healed yet. That means it's the most recent. And what I'm trying to tell you is, I am suggesting it is the one responsible for the most recent Jupiterian stripe scores on our planet. And that tells us that it happened within the last Jupiterian period, which would be the period we currently live in, which is the Jupiterian Nine Stripe Period. What do I mean by that? Well, because 2 stripe scores before that, we had 11 Jupiterian stripes. Theoretically, 4 Jupiterian periods before that, we had 13 Jupiterian stripes. What does that tell us? Well, the more Jupiterian stripes you have on a terrestrial planet, it tells you that the planet was rotating much more quickly back then. So we have decelerated from 13 Jupiterian stripes to 9 Jupiterian stripes over the course, roughly over the course of 4.4 billion years before present. And that's only judging it based on the rocks that we find in Australia. Earth might be a little bit older than that in terms of its solidification after the planetary sutures came together. That's right, planetary sutures, just like a baby skull. Planets are all gooey, and then they come together, and then that skull kind of like fuses together, and that's the planetary suture. Don't ask me where we might find one on the Earth. I don't know if I could find one yet. But anyway, back when the Earth became solidified, we're only tracking that age. We have no idea how long the Earth was a molten ball and it probably looked like a brown dwarf. Well, that's funny. I wonder if that's possible. I wonder if brown dwarfs really aren't stars. Okay. I'm just wondering, I don't know. So anyhow, we have our counter rotation going on here, right? And that's what creates this wave that comes down here. And as it comes and gets closer and closer to the North Band of Basin vortex or vortical core, it whips into this fashion here and picks up this huge current, just like the rapids in a river, man. It picks it up and it makes this, it helps to develop this pentagonal shape right here in North Band of Basin. And that pentagon, as we learned from looking at from the scientists also, this, I'm not pulling on my butt now, okay, you would have had 5 smaller vortexes. You're not going to get that kind of activity in the crust of the Earth, ladies and gentlemen, unless something is extraordinarily fluid. This is not something that takes billions of years to form. This happened, bam, just like that. Like I said, if you're on the ISS, you're going to see that wave going across the ocean. Exactly the same way that we were sitting in our seats with NASA as we were observing the video of the what's that thing called? Help me out here. The Eureka moment. Hello, 2010. The global tsunami going across the face of the sun in the plasma along the coronal layer. We're standing there watching it. That's what happens on Earth. So, and it's from that video that it's helped me come to understand that this is extraordinarily possible, and I'm totally with it. I just want to try to get everybody else with it. I swear I feel that people are laughing at me right now, the scientists. That's not plate tectonics. Yeah, but hopefully somebody out there will listen to me and take into consideration what it is I have to say, because it makes sense, it's logical, and it works. Take, for instance, this. I don't know if you can see this. I had to draw a diagram because for the life of me, I can never remember which circle goes in what direction. So North Band of Basin, I didn't have to worry. That one's like, yeah, that one rotates, boop, that's like that, yo. And the Pacific Oceanic vortex rotates. Yeah, you got that one. It's rotating counterclockwise because it's basically tearing the Baja California and all that stuff away from the North American continent. Very complicated stuff. All right, so. Man, that was 15 minutes and I haven't even gotten anywhere yet. Okay, moving right along to the next slide. Here we go. Here's a better picture of it, right? Now, this vortex spun so quickly, ladies and gentlemen, as everything filled back into it, that it ended up going to this center here, which if I were to take that pin right there and do the same kind of a circle here, but move it over here, it still has a circular form that fits. And basically what it means is the object hit here, and as it filled in, it moved over to here. Why? How did it move? How do I know it moved over here? Well, because this is the foamy crap that this little thing right here, that's the foamy crap that gets toward the middle after, kind of like all that foamy stuff in the toilet bowl when it's going down. All the toilet paper gets all right toward the middle, right? That's the toilet paper. All right. Going to the next one. Yeah, okay. Now we got a bigger view, and okay, all good with that one. Now I showed you everything I'm doing on those. Okay, now we're going to this one, right? We're going to get closer pictures here, and I'm going to tell you that all these little things going around here, all those bumps, Spratly Islands. Spratly Islands are actually blast ripples. So basically, when you're dropping a very small pebble into the water and you see all these little ripples coming out of it, in essence, those are blast ripples, even though there was no blast, right? Maybe there was no blast when this thing hit. Maybe it was just one great big and it liquefied everything going around it. This impactor did in fact affect the planet in such a way that it set the planet into a state of worldwide liquefaction, which I'll explain later. Okay, now we have a different view here. Basically the same thing, but what's different is my measurement of the radius of my blast ring, I think. Yeah, because that's yellow and this is red, so this is the one we're looking at. I did it again. I couldn't figure out what I did with my other PPT that I just showed you. So I have that problem every now and then. So there it is, Spratly Islands right there, yeah. Alright, moving right along. And now we're going to go back up here. Boop, doop, doop. Okay, just a bunch more of the same thing. Okay, here we have another one of the same thing, only north is way the heck out here. Not really sure what I was doing now. Okay, now here we go. This is where I'm drawing the B2W. So you take the B2W, you draw your line from the right, you know, in this case, from my point of view, this is my left. So I'm going from my left all the way down over here to the rightmost limit, and I'm drawing that line as it comes in. Believe it or not, most of the impactors on our planet appear like this. Most of the impactors on our planet appear like this. Hello, please work with me here. Okay, they don't all hit like the moon. Okay, don't just assume that because there's no central peak that it couldn't possibly be an impact site. It's the wrong answer. This is an impact site. This is what happens when projectiles hit the ground on our planet. And then you take this line and you draw a line straight through the center of it back this way. So as a high angle, this is high angle by the way, as a high angle impactor comes in like this, it comes in and hits the ground and goes bam, and it comes back. Comes from this direction, hits the ground, bam, goes back. Low angle, coming in at like 30, 40 degrees, hits the ground like this, goes boo, boo. All right, bam and boo. Get the bam and boo right. Okay, so we have bam and boos. All right, now I'm going to go to Google Earth, right? And so here's Google Earth. Here's all my vortices. This is the Arctic vortex. This is the Sipaliwini vortex, the Pacific Oceanic vortex. Notice how it's going right. Ooh, imagine that, right straight through there. It comes right out of San Francisco. That is so weird. Oh my God, that's terrible. That's, I mean, terribly cool. There's the center of it. The reason I got this one, I didn't find the center because of a vortex. I couldn't find a vortex, so it must be covered by, I think I might have found something that looks like it, but I had to use the other terrains on the planet to figure out the vortical cores. And this was the toughest one to figure out right here. I was like, what is going on? All right, then it finally made sense later on, right? So then you have, so this is the North Banda Basin vortex. Then you have the, Lake Victoria vortex, right? And ladies and gentlemen, I am so sorry, but I totally get confused. Who's rotating in what direction? I never get confused on the Pacific Ocean because I am so familiar with the San Andreas Fault. But these other guys, yeah, go figure, right? So it just so happens that these guys are rotating sometimes in a different direction. Now, I was earlier suggesting that these two, that the South China Sea impactor, when it impacted, forced these two continents to separate by their rotations. I was wrong, because in actuality, if we go down here and we look at Lake Victoria, boop, notice this, circle, well, work with me here. I mean, the center of the vortex is actually right here, but if you go, it goes from right here. Why am I looking at a spiral, ladies and gentlemen? This is a spiral density fracture that just happens to be a river. That just doesn't happen because the Earth is round, okay? It happens because there's a vortex right there. That's what I'm saying. If the Earth ever gets liquefied, or, hits a state of liquefaction and all that, stay the hell out of this lake. Don't go fishing there. and it goes around like this. That tells us that this continent is rotating clockwise. It rotates in this direction, which is why this stuff is blowing out the other way, just like our galaxies do. All right, you see that right there. Now that's what we're doing, folks. It's going clockwise. See, going clockwise, which is the opposite direction, which means if what I was saying was true and the impactor made these continents rotate because of the vortices, they would have rotated and collided together. Now that starts a whole new can of worms, and it's like, man, I know what it is, but to explain it is so much more in deep detail and depth of discussion. I will explain it in this particular series for this particular impactor, because this impactor had such a huge effect on our planet all the way around our planet. Okay, so it's there. It's all there. I can explain every last bit of it. I'm gonna cuss. Tied my tongue. Okay. So this one's going clockwise, and I was like, well, South America is going blah blah blah. No, it's not. No, it's not. If you look at the Sapaliwini Forest right here. Hello, come on, Google, work with me. Okay, here's my little spot right there, you see, and wow, it's just like, see, it's just like, oh, there's the Amazon. Oh my God, the Amazon is it. Oh no, no way, it is. Yeah, it's a spiral density fracture. Ah, it's going that way, and it's splitting the continent apart. That's interesting. So what does that tell us? That tells us that South America its vortex is rotating in the counterclockwise direction. Now, if you take your little diagram right here and you figure out all the different rotational directions with these guys, and you know that little paper thing we always do, you go, it says you like Tommy. Oh no, it says you like Bob. Okay, well, you do that with this, and then you go, and you put each of the opposite circles together with their arrows of rotation, and suddenly you have something that works like this. This is the, let's say, for instance, my hand rotating here represents the North Pole vortex, or the Arctic vortex. This one represents the Antarctic vortex. Notice if you put them side by side, they're rotating like this. But then if I turn them around and put them end to end, now they're rotating like this. And now my fingers are rotating in a manner that is bringing them closer to me around each time. I guess it does. It's really hard to say. It would be closer to me the other way too. But it's going like this, right? And then they're going like this. They're doing opposites, because if they were the same, they'd be going, I don't even know if I can do the same. Yeah, there it is. See, and they're not doing that. So, I'm amazed with myself. I actually made my fingers do the right thing. Okay, here's another thing, folks. Here's Antarctica, right? Antarctica is rotating counterclockwise in the exact opposite direction of the planetary rotation. Now, how do we know this? Well, it's vertical. Why is it vertical? Because it's like a galaxy all its own. Look at this. Yeah, you know what that is? This is Antarctica's most prominent spiral density arm. It's its most prominent spiral density arm. And it's rotating this way, and this one is rotating this way. And that's why we get the drag the rope shape of where it's just going out like that. It's not the only one. I mean, this is actually a spiral density arm right here, believe it or not. It's just really hard to see it. And this one is one here. So you have 1, right, 2, 3, 4. Oh, this one's here. So you have like this one here. This is 3. This one's 4. And yeah, I'm really not quite sure what all that is. All right, so you have like 4 spiral density arms. And each one of them extends out with spiral density fractures. Well, you see this one's spiral density fracture goes, and it's also umbilically connected to South America. Woohoo! All right. I guess I'm not going to get to all of the effects. It's already 3:27, and I have got to go to work. Oh, what a drag. Oh, no. I'm sorry. Did I say drag? I love work. So in case those people are watching me. It's like, I doubt they do. Nobody watches me. Mm-hmm. So there you have it, folks. I described basically how this is working. One thing that I do want to talk about. The reason I said don't go fishing in Lake Victoria is because all these equatorial vortices are anticyclonic. When I say anticyclonic, I'm telling you that they suck things from outside in toward the core of the Earth. And as they're sucking things in toward the core of the Earth, they're spitting things out through the poles. Sounds familiar, right? Sucking in at the core, spit it out at the poles. Kind of like GRBs get spit out at the poles. Well, it's because centrifugal force takes the energy and forces it down the surface of the body, and then it gets cycled back up, trapped inside of that shell of energy, back up until finally it's so packed with energy it builds up at the poles and gets pooped out of the poles. It's the same thing here. So when Earth began, Pangaea came up to the top of the Earth, and Antarctica was at the bottom. So Pangaea wasn't the only continent. Antarctica has always been at the bottom. And Australia, even though it's sitting over here right next to the North Panda Basin, was also part of Antarctica. But it's been, because of centrifugal force, it's been moving toward the equator. Okay, now that's it. Now, how do we know that the Earth is the bottom? The bottom down here is affected by a greater gravitational force, the one that is galactic. So galactic gravity is what makes the Earth have a bottom in the South Pole, and solar gravity and planetary gravity is what affects the equator. Okay. All right, enough of that. Watch out, Booms. I gotta scoot my chair back. Okay, it was nice talking to all you guys there. Hopefully I covered enough information to say something. Let's see. Do we have anything up here that we wanted to talk about? Yeah, pretty much. This is my little diggity-doo here, showing you. See, I was telling you about the same rotation. So the arrows of these two here. So at least, even though I keep getting confused, I wasn't confused when I put this together. Thank God. Okay. Yeah, there you go. See, notice South Pole, North Pole going the same direction. Africa, Pacific Ocean going the same direction. All right. That's it. We'll go ahead and hook this one up and plug it in someday. All right.